So we start the first chapter, say introduction. This one is, I say, to me it's a little bit boring because there's a lot of definition. So there's a lot of symbol, a lot of definition we will use in a class afterward. So let's start. So introduction. We first start with Euler's formula. Euler's formula means there is a very, in mathematical world, this one is called one of the most beautiful equation. Sounds very nerdy, I say, sounds very old-fashioned, but equals this data can be x or y or whatever. So what it says is this is Euler's formula, which is very simple and very understandable, but very hard to find. If you see several critical or well-known formulas in mathematical world, like other words, you will find out that they are actually very, very simple. Their formula is very simple sometimes, but simple formula is very hard to prove, right? So this is a very, very simple equation, but one of the things very hard to prove. Because for proving in mathematical world, I'm not a mathematician, so I just imagine how they feel. You have to prove for every cases, right? You can do it either way, like you will find out something not meeting the equation. That's simpler case. You can find one example that's not meeting the formula. That's all. That's game over. But even though you find some cases meeting the equation, but you cannot find but if you cannot find all the cases, that's not proving the equation. So that's the reason sometimes it's hard to prove the equation. Also, I hear that over 10 years ago, I heard that I think Chinese mathematician tried to prove that 1 plus 1 is 2. He succeeded. 1 plus 1 is 2, right? But how you can prove it? Or when you go to your elementary school age, 1 apple plus 1 orange is 2, right? Kind of thing. But when you try to solve for all the cases, it's very difficult. So I think the Chinese guy successfully proved that 1 plus 1 is 2. And now he's solving 1 plus 0 is 1. Sounds okay. Let's go to the lecture. Anyways, so this is the Euler's formula. Euler's formula. So why this one is so important? Why this one is so important? One of the reasons is this one gives you an idea that how we can draw, how we can plot complex number. One of the way. So you may familiar with those plane, those axes, which is shown in here, real axis, imaginary axis, and you say you have a complex number of a plus ib or a plus jb. You will say, okay, there's a here, b here, and here is the complex number. You know that, right? So this one gives you an idea that this is totally complex number. This e, I theta is totally complex number. This cosine and sine, we can divide them to real part and imaginary part. So this one gives you one way to change the complex number and segmentize it, separate them into real number and purely imaginary number. Using that, we'll find what's the x value, what's the y value in this complex plane. So that's the reason this equation is very important in mathematical world. So this is a review. For complex number, they can divide into real part and imaginary part. And we call them real part and purely imaginary part. Sometimes this I, which is, I think it's come from imaginary, I'm not sure about it. This I can be changed to J. So I and J will be used together in this lecture. So, example 1 plus 2I is a complex number. In Euler's formula, that's like this, right here. And how we can draw it. Let's go back to the complex plane. Let's try where is EJ theta. Of course, based on Euler's formula, we know that there's cosine theta plus J sine theta. Okay? If you say this is A, this is B, and you plot it, A is cosine theta, B is sine theta. So EJ omega is right here. Square of cosine theta, which is square of cosine theta, and square of sine theta. Sounds familiar, right? If you add them together, what is it? Is 1. Right? So what it says here is, if you, the absolute value, the distance from the origin to this Euler value, they are always 1, right? So the thing in this Euler equation, they are distance of 1 from the origin. What is the symbol representing a constant distance from certain point? Circle, right? So we introduce a concept of unit circle. I'm sorry, this is not circle, looks like, but it's circle, believe me. -1, 1, -1. So this unit circle, that means if you have this Euler equation, there will be any point on this unit circle, right? That's one of the most important concepts we will continue to use in a later. So conceptually wise, this one bridges complex number. They separate them to real and imaginary parts, and they all locate in the unit circle. And a sub equation, how to find their real part? Cosine. How you can find it? If you add theta, if you add minus theta, this minus theta make this one minus, right? So if you add them together, they will, if you add E j theta, E minus j theta, you are adding them, this cosine theta twice. This one we cancel out, plus minus. So there will be cosine theta if you divide by half. To find sine theta, we do the same thing. Now we have to subtract to cancel cosine by maintaining sine. But what left over is Ej sine theta. So we have to divide by 2 like this. Let's change the value. So that's a summary of the equations shown in here. You can see that Euler equation, if you to find cosine, which is a real part number, just add them together, divide by half. Sine, imaginary number, which is minus, divide by 2i. That's so complex, right? Questions? Nope. Nope. So let's bring out these guys again. So remember how they looks like. So EIX have a form of EIX, right? You can find them always in this equation. This is previous one. So this is equation defining Fourier transform. You'll find them in here. Let's forget this minus. Ej, which is imaginary number, omega t is theta. So this one is based, I cannot say based on, but they are utilizing or similar to Euler's formula, Ejx. Also, if you go to this Laplace, you will see that E minus ST, right? So this one is also same. Don't forget this S is complex number. They have this ES. Let me clean this too complex. EST or minus ST. You know that this S is complex number, right? So this S can be A plus B, J, looks like that. Okay? And then they will be EAT times EBT. If you switch this S with A plus BJ, because this plus in here, we can divide them as a multiplication. So AT becomes like this, BJT, where I switch the J to the front, JBT, so they looks like that. So how it looks like? We only adding this term to our Fourier series. Once again, explain this. Of course, all of this, my explanation is not really formulated equation or method, just the way I understand. So this may be sometimes wrong, but this is how I understand, how I can follow. I try to understand what's the difference. Because a lot of, when I learned for the first time, I think that they're totally different equation, but actually they're actually very, very close and very related. So I try to explain that. So in Fourier series, we are using E minus J by T. This is X in our case. In case of Laplace, we have E minus ST, and they can be divided into E minus AT times E minus JBT, right? And then this and this are very similar, right? So we can define them as, we can think them as Fourier series is Fourier series. Laplace transform looks like some scale factor, how the amplitude change, scale factor times Fourier transform. You can think in this way. Of course, my current explanation is wrong because this scale factor is not outside of this integration. They're inside of this integration. So we cannot exactly say, this is a really scale factor. But we can think that the formula, let's say there is function, there's a function inside here, which we try to change. This function is scaled. Here is just f. There's f times EAT, so they will be scaled. Inside this integration, you can think it this way. That's the reason I first introduced Euler's formula and then talk about that. And we will come back, hopefully end of this class or maybe early of next class, how this EIAT works, how the EAT works. Next page. Okay, let's go back to a boring case. In this lecture, we have several definitions. very hard to go back and forth, but let me use this one for a minute and then I'll go back to there. So we will say these symbols are not always true. I will say these symbols are not always true. But in our book and in our lecture, I try to define in them this way. First, not yesterday, 2 days ago, I explained that there is a continuous signal and we can sample them to find out discrete number. Once I explained that, there is continuous number, but like a computer, we cannot use continuous case. So you have to pick values at such a point. That's called sampling. We sample it. So we pick this value, we pick this value, we pick this value. So actually the data looks like a discrete kind. There is space between the data. There's a discrete signal. So if you see small x, round bracket, t, that's continuous signal. If you see after in this lecture and this book, if you see this, that's continuous signal. If you see same x but rectangular bracket with n, that's discrete signal or sampled signal. Pretty clear, right? You can think also in this way. This t is time, right? This time is continuous. N is 1, 2, 3, 4. That's integer number. So this n is discrete number. 1, 2, there's a lot of real number between 1 and 2, 1 and a half, 1 and 2, 1.2, things like that. So that's how you define it. Also, on Monday, I explained that we are trying to learn, one of the major objectives of this class is we try to learn how to connect, how to bridge between discrete time and frequency domain. If you see small x, small character, that's time domain. If you have capital, large X, that's frequency. So in small x, we will use time, we can use n. In frequency domain, we have to use frequency. So this omega, this s, this complex number has a frequency term. We can define them like that. So in short, t, round bracket t is continuous. Rectangular bracket n is discrete or discontinuous. Small character is time. Large character, capital, is frequency. So straightforward. Okay, so we have several examples about signals and systems. So actually many systems are driven by corresponding signals. Say our system can be car, circuit, device, control system, communication system, power line like a power supply, or even human body. There's a system. I once defined that yesterday, Tuesday, defined that signals are either input or output from the system. They can be stimuli exciting the system. They can be response coming out from the system. So for example, if you have a car, very simply say, we give a force to drive the car, right? That's either by engine, either by battery. And there is a pulling force, like a friction force, repelling. They try to not to accelerate the car. So in short, we have a force, which is a stimuli, which is exciting the car, the system. But one of the response is what? Moving the car, the distance of the car. But also, this friction force is working. That's how we define it. So there can be force, velocity, current, voltage, blood in human body, sound, light. There's a lot of forms. Let's think about, let's show, this is repeating, but let's have an example of continuous and discrete time signal. This is continuous time signal, which is continuous by time. This is discrete time signal. But discrete time signal is a little bit looks different from what I showed before. We have xn in n is, I say, integral, right? So they can be 1, 2, 3, 4. But they can be 0, minus 1, minus 2, minus 3. So you can see that there's a value x0, x1, x2, x3, x minus 1, x minus 2, x minus 3, things like that. So in continuous time, they become continuous like that. Discrete time, they can be symbol like there were a dot at the tip, and there is a stem coming from the dot. So you can define them like that. So let's have several representation of signals. The pictures used here is coming from the book. So we have a copy right over there. Say that this is our original signal, xt. If you have xt minus t0, how that looks like. Of course, they are on the screen, of course. So say that we have a signal, say xt. That. If you want to know that this one is shifted to here by, say, t0. How we can define this yellow signal? X, something like that. So we know that we can think in this way. They are moved to this plus side. So we can think that this signal, the Y signal, is delayed. Right? They're delayed by t0. So we can also think them that delayed. You can also think them as time shifted. They shifted by time. They shifted in the time domain. This is called time shift. And we define that. So we have to change these time symbols, and we define them like this: t minus t0. So this minus t0 means we have to wait. The signal start, say that this point start at time of 0, but to start this same signal at this yellow signal, we have to wait t0. That's how they define it. So this one is also called time shift. Another one is reflection, time reversal. So let's use the same Y signal. If you have the same signal, but they are reversed by time, how we can define it? Of course, you can see the picture. It's a better picture than me. So basically, this white one and this yellow one is the same or symmetric of this y-axis. This yellow one, we can define them as minus t. That's called time reversal or reflection. So basically, they're same, exactly the same, except they are facing each other by this y-axis. Also, time scaling. Time scaling means, this is a sometimes interesting part. Let's say we have a symbol like this in time. If you have a question that what is x2t? If you have this question, of course they are shown on the screen, how we can find it. So before we first start we shift by time, by subtraction, also we reverse by time. Now we scale, we change the amplitude in x-axis. Let's think in this way. Say that this is 2, time of 2, and to reach 0, we have to wait for 2. In here, we only need 1 to make 2 in here, right? That means that the wall looks like this. So how we can do it? How we can find out? We can see that they are shrinking down, squeezing down in time domain. If you have x t divided by 2, we have to wait like 4 to reach 2. So there will be extended like this. So if you have multiplication, now we are using multiplication in time, 2, half, 3, 5, 5t, whatever. If you change the multiplication of the time, they shrink or extend in time domain. This one is called time scaling. This one is pretty straightforward, right? Straightforward, really. But if we go to the frequency domain, something interesting happens. We will cover in chapter 4 or 5, I believe. But before we go, I'll give you a little taste of it. In short, we will have always have 2 plots. One is time domain, one is, I don't know, frequency domain. We always have 2 plots in time and frequency. If you have a pulse, like this rectangular signal in time domain, in frequency domain, it will look like this. This is called a sync function. If you have, let me draw together. Of course, this is not scale. This is not exactly the same, exact picture. Let's have a concept. If you have, so this one is corresponding. If you have in time domain, if you have this sync function sync function in time domain, their corresponding frequency domain signal is rectangular. So this one calls similarity or things like that. If there's a lot of similar things happens in time and frequency domain, if you have this rectangular signal in time domain, you will have sync function in frequency domain. If you have sync function in time domain, you will have rectangular function in frequency domain. But one major difference is existing here. If you try to extend the signal, if you try to extend the signal by time scaling, this one goes to the opposite way. This one will shrink down. So in similarity means there is a, if rectangular, zinc, rectangular kind of corresponding together. This is not chapter 1 case, so we'll cover again later to give you a taste. But if you, why we learning the time scaling? When they're changed by time, time scaling happens, the direction of frequency goes to the opposite way. If you, of course, if you shrink down, this won't expand. Also, the amplitude changes. Well, let's cover it later. But in short, why are we learning that? Because to understand this characteristic in later chapters. Questions? Too shy? No. Okay, let's move on. Okay, periodic signal. What is, when you think about, when you are asked, what is periodic signal? What kind of signal you can think about? What kind of signal comes out from your brain? Sine? This is a periodic signal, right? Sine is periodic. Why this is periodic? We can think that they are repeating. They are repeating after certain time. What is certain time? We can define based on this, right? It's for the frequency of one divided by frequency. That's a period. So we can think that they're repeating by certain time period. And we define periodic signal in the same way. I say repeating at a certain time having a period of t. But when I learned the signal and systems class, I sometimes misunderstood a little bit because I thought that like sine wave, they keep on waving like this, but actually they are not. Let's see the first example. The first example, this shape is keep on repeating, right? So that's pretty understandable like this. But this one is periodic in frequency domain, in this one. This one is periodic. A little bit hard to understand. Of course, you know that they are in this slide, so you know that it's periodic. The answer is already given. But when I first see this signal, hard to understand because something looks repeating, but not so repeating in a normal way. So in periodic signal, I say there is a set. There's a set of signal keep on repeating by a certain time. So let's go back to here. A set of signal is repeating at a certain time of t, right? In here, the bottom one, we can think them as up, down, one, up. This set is keep on repeating by this time period. Can you find it? So this periodic signal, what we have learned by far is normally sine wave, wavy continuous time, continuously. But they can be discrete. They can be discrete. But anyhow, a set of signal, set of this snowman looks like shape is keep on repeating. Also a set up, down, one, up is keep on repeating by period of t. So especially the discrete time signal is hard to see if this is periodic or not. One way we defined here is if there is signal, they're always true. If they are always meeting this equation, which is let's say plus, right there. That's the definition of periodic. What this one says here is a set of signal, which is called ft, is keep on repeating by period of t. A set is here, a set is here, a set is here by spacing of t. That's how we define periodic signal. Got it? Okay, another one. even and odd signal. Even is what? 2, 4, 6, 10. Odd 1, 3, 5. Right? But I feel that it's a little bit different here. Even means they are time reversal. Let's remember that. And here, time reversal reflection. They are symmetric from this y-axis. They are symmetric. So how we define it? How we define it? We say that's our symmetric y-axis. Right? In here, even signal, looks like a mountain, looks like pudding, I don't know, but they are symmetric along this y-axis, right? So we can define in the same way. This one's called even function because they are kind of looks like symmetric. Even is 2, 4, 5, 2, 4, 6, so they're always paired. So plus and minus are paired. Odd, we define them similarly, but we have a minus here. So what this one looks like. There is a signal, but they are not really symmetric by y-axis. They are symmetric but reversed into x-axis also. So this one is how we called odd. Okay, so that's definition. If we have any arbitrary number of x, say some function, say x, we don't know this is even or odd function. How we can find out even part and odd part of here? If you add them together, add is minus. If you add them together, assume that this is even. Assume that this one has some even part. Let's change it. Let's change. Let me start again. This one has some even part plus some odd part. It always happens. Sometimes they are mixing together. How we can find this even part and odd part? If you take minus of it, if you add them together, what happens? This even part, they are same to, they are same, right? This odd, they are same to minus of minus t, based on this definition, right? So, if you add them together, this even part will be added together because they're the same. This odd part will be subtracted because they're plus and minus. So only 2 times of even part you have over. So how you can find even part? You simply divide them by half. That's your even part. Right? If you add, not adding, but subtract them, this part is the same but minus. So they will be cancelled out. This part minus, 2 minus will be plus. Right? So basically this odd part will add it together. So there will be 2 times your odd function, which is if you divide by half, there will be your odd part. So that's how we define, how we can find out even and odd part here. So similar to our Euler equation, right? In Euler equation, to find real part, we add them together. Imaginary part, we subtract them. Only difference is there's complex number, we have j or I in the denominator. That's the only difference. Okay. So when I talk about Euler formula, I briefly mentioned about this, but let's go to the complex signal and what happens. Any questions by far? Okay. This one has 3 parts. This one has 3 parts. Okay, I put number 1 over here. Number 1, number 2, number 3. They become more complex. First case is continuous time, complex, exponential signal. This is actually covering all of them. And let's think how they look like. First case, assume that we have this signal. In general form, this C can be complex. This A can be complex. But complex does not mean that they're always complex. They can be real, they can be only purely imaginary, or real part plus imaginary part. First case, let's say both C and A are real. They don't have any imaginary part. Real number is part of a complex number, right? So we can define them as real. So say that this C and A are real. That's case number 1. How they look like? If C is real, A is also real, we can think them as just simply say real times EAT. How they looks like when you plot in time domain. In time domain, well, exponential, right? So they will be shown as exponential like this. At time of 0, this one becomes 1 when time of is 0, when this one becomes 0 when t equals 0. Not 0, what I'm talking about. This one becomes 1, time of 0. So this function will become c. So in time of 0, there will be c, right? Why there's 2 pictures shown in this slide? One is like this, the other looks like this. I think I always break two of these on per lecture, but anyways, I try to lower my strength a little bit. What's the difference between these two? Let's think about A. These 2 functions has 2 different A's. Say E minus T. How they looks like? ET, they keep on increase. So this one goes, this white one. E minus T, when time goes, they will decay, right? So this one goes to this red one. So when A is other than 0, they will go like that. When A is lower than 0, it's like this, right? So exponential, 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 but depending on C, they can be here, they can be here. Depending on A, the polarity of A, they will go like this, they will decay, they can be expanded, depending on how it looks like. Simplest case. Now, what? So now, let's make them a little bit more complicated. Second case. When C is constant, real, and A is imaginary. So C is still real, A is now complex or imaginary. Now, let's say A is only purely imaginary in this case. We can say that xt, C is constant, right? But A is now imaginary. Let's say they're purely imaginary. So let's change them as E, J, right? Omega 0, T. J omega 0 is purely imaginary. So let's say our A is J omega 0. How we find it? How we find it? Let's go back to Euler. Let's go back to Euler. C is real. E j omega is cosine omega 0 t plus j sine omega 0 t. Right? So we have periodic signal and periodic signal. So let's first find out how that looks like. If you add a period of t, this one becomes c times cosine omega 0 t plus t times j sine omega 0 t plus t. There is certainty to make them together. What is the t? To be the same, let's pick this one. Cosine omega 0 t plus small t large t, to make them together same. To make them together, this one should be an integer number of 2 pi. Is it right? Okay. So to do that, so what's the t? Omega 0 times 2 pi times n. So n can be 1, 2, 3, 4, 5, whatever you may do it. What is the fundamental frequency? Smallest positive t when n equals 1. Right? That's called our periodic signal, because this t can be 2 pi divided by omega 0 times 1 times 2 times 3. But remember, the periodic signal, they are repeating a certain period of time. Remember? So say that, let's go, maybe it's better. Let's go back to this periodic signal. We can think them as repeating by every t, right? we can think them as these two sets. You see, this two set is repeating every 2t. Remember, 1, 2, this two set is repeating every 2t, like this. We can think them as the 3 are repeating every 3t. That's how those large n explains. But in our definition, we just define them as smallest one. Because we know that even though we say the smallest t, they're repeating smallest t, our signal doesn't change. So we define them, period, as the smallest one out of this n. So this is our period. When you plot it, how it looks like. So in short, this is a periodic signal. Periodic signal. If by 2 by omega 0, 2 pi by omega 0, they're repeating by that. So how we define it? How we define it? They can be sine wave. Sine wave. Cosine, sine, so they can be sine wave, right? They can be scaled by A, depending on the C. So they can be sine wave, like that. Period of 2 pi divided by omega 0. What will be next? Of course, you can think that. Number 3. When both C and both A are imaginary. So C is imaginary now, A is imaginary now. So become more complex, complex, complex. So we can define C as we can define as C is imaginary number. We can define them as E, J, zeta. We can define A as also imaginary omega 0 t. So you can think them in this way. This is sine wave. We already derived, right? Sine wave in here. There's sine wave. Now, previous case 2, C doesn't change by time because C is real number. So C is constant here. So it doesn't change. Now C is imaginary number. So they can be changed by time. Okay? So now, depending on how we define it, it can be, remember, first case we have decaying signal, or we have omega signal. So we only have top part. We put them symmetric in x-axis because DC is scale, right? DC is scale. How the maximum amplitude that looks like. And then, because of the sign, they will be oscillate between this exponential line. So, mathematical wise, if you just put the number, we can find it very easily. However, one of the important message here is it can be diverged or it can be converged. This divergence or convergence concept will be used to define if you can find Fourier transform or not. What it says here is, for example, this one, they are decaying, right? So as time goes, when time goes infinite, we know that they can be converged. They can be converged to a certain point. This one is divergent. they are exponentially growing until they become maximum or maybe infinite, right? Exponential is infinite, go to infinite. So in this case, we know that if you keep on tracking this value, we'll find out the final value when they settle down. This one we cannot find. So in especially Laplace transform, in Laplace transform, don't forget, in Laplace transform, I say EST, right? They can be divided into real part and imaginary part, right? If this one is diverge, because this A is minus, if it is A is minus, the value will diverge, right? In this case, we cannot find what's the value because they are diverging. So in this case, we cannot find the Laplace transform. So in Laplace transform, we will introduce a concept called reason of convergence. Reason, the value or the reason in complex plane where they converge, the reason that they converge, the reason that they will diverge. In this area, we cannot have Laplace transform. In this area, we can find Laplace transform. So Laplace transform is given a simple equation like that. We keep on using S in our mathematical or engineering world. Sometimes Laplace transform may not exist because of this divergence. So this divergence concept is pretty straightforward because exponential AT, those parts coming from here, we can see that depending on the polarity, you can see that they diverge or they converge. Mathematically pretty straightforward, but we will use them in Laplace transform to define the Laplace transform can be existed or not. In previous lecture, I briefly mentioned that Laplace transform has more broader meaning than a Fourier transform. Fourier transform is only imaginary part or inside unit circle. However, Laplace transform covers all of the plane because A plus J omega. They can cover all the plane. Actually not. Because of this convergence issue, of this divergence issue, there is several areas that Laplace transform cannot exist. So that's the reason we are learning this. Okay? So we will see a lot of E, A, T, E, J, omega T kind of things in the next lecture. Questions? Okay. Now we define two functions you may already know about. One is called unit function, unit step. The other one is delta function. So unit step and delta function. Unit step means in time of t, defined as u, this one is 0 when t is smaller than 0. This one becomes 1 when t becomes 1, right? Right, okay. Just in case I forget. So simply say that's unit. So when t is 0, below than 0, they become 1. After t becomes 0, they becomes 1. So before then, they're 0. After that, they become unit of 1. In discrete time, I say rectangular n, their same meaning, they becomes 1 when n from when n is 1, 0, 1, 2, 3, 4. They are 0 when n is equal to 1, 0. So in the plane, they are 0 until n is minus 1. And when it's 0, they suddenly become 1. They're 1, 1, 2, they become like this. Of course, now this is hard to see, so we put a stem at the bottom to see how it looks like. So the only difference is they are same concept, below 0, 0, larger than 0, 0, 1. Only difference here is there's a lot of point in here, but there's only one point, minus 1, before 1. So we exactly find out when they becomes 1. In case of delta function is what? Delta function is let's start with a discrete case, it's simpler. Delta function is what? They are 0 when n is not 0. When n becomes 0, they become 1. So, like this. Okay? Also, in discrete time, this delta function can be represented as delta n comes u n minus u n minus 1. Why? Because u n minus 1 is what? We shift by time. We shift by time, right? So if you shift 1, unit of 1 in time, what happens? Think this way. Now, when when n is 0, they becomes 1. In this function, when n is 1, they becomes 1. Right? So they are 0. Even though n is 0, they're still 0 because they are 0 minus 1, so still minus 1. From here, they becomes 1. So if you subtract this one, the white one, by this one, red one, other thing is overlapping, so they will cancel out. But only this one at 0. White one is 1, but red one is 0. So we subtract them, we only have this. So how we define the delta function. In continuous time, we do the same thing. Delta function is given as they are 0 when t is not 0. They become infinite when t is 0. Something like this. How we can define it? In here, I will say another difference between discrete time and continuous time. In discrete time, we will use subtraction. When in continuous time, we will use differentiation. Remember, differentiation is defined as, how we define differentiation? When you have some signal, how you find their differential? Memorize? When you start, you say, okay, I take the point here. So let's go with the programming. Let's go back to programming. If you try to find the slope of a function, how do you find it in the programming? You pick one point, you pick second point, and find the slope between these 2 points. Say this is the function of y. Say you have y 10 minus y 9 divided by 10 minus 9. There's a slope. And if you make them space smaller and smaller and smaller, we'll find a slope at a point until they go to infinity small. That's how we define it. So you see that this subtraction and differentiation has very close relationship, except this differentiation, because it's discrete time, we only have a point. So we cannot define differentiation. We just have difference or subtraction. In this continuous time, they are continuous. They are continuously spaced. That means there is infinitely small space between each point. So the difference or subtraction become smaller, 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 smaller until they reach the same point. That's the differentiation of the slope. So this differentiation in continuous time is corresponding to subtraction in discrete time. So you will see similar equation in discrete time and continuous time. Only difference is subtraction versus differentiation. Okay? Anyways, as this subtraction is corresponding to differentiation, you can define them as like this. Because this slope goes to infinite at the point, and then the slope becomes 0 again. So slope is 0, there's sharp increase in the slope, and then they become 0 afterward. So this one can be defined as like this. This is mathematical meaning. Why? Can you have infinite amplitude of arrow in here? So this one says other than 0, they are 0. At 0, they become infinitely long. Mathematically, right? But conceptually or physically, is it right? Can we have infinitely long line at 0 point? No, right? Also, you may hear that when you go back to your high school age. Let's go back to high school age. When you first learn the differentiation, you will see you have this. You may remember this. To find a differentiation or slope at a certain point. Do you remember that? To have, you may remember that to have a differentiation at a certain point. When you differentiate from this side, they should, so slope-wise, they will be looks like this, they will look like this. The slope should be matched at the point, right? If you come from left, if you come from right, if those two are same, then we have differentiation. That's definition. If they are not matched, if they are not, if they are not matched, we cannot have differentiation. In here, what happens? In here, we have a slope, we have positive infinite, and then we go to 0. From here, we have 0, negatively infinite slope, and go to 0. So in mathematical wise, even, we cannot have differentiation at this point. Just definition here. this definition. So people try to understand them in this way. So this is just for fun. Just for fun. We are not make infinitely sharp impulse. We are not making it. We give a very small, very stiff slope, but not infinite slope. That's we define as unit function, and then this slope is our unit function. And then they define this one becomes infinitely small to go to our delta function. So how delta function looks like here, they are constant slope from 0 to delta, right? 0 to delta is constant slope. So differentiation from 0 to delta is constant value. So you'll see that there will be a constant value of slope between 0 to delta. When you make, and the slope is 1 divided by delta, right? 1 is y, delta is x, so 1 divided by delta is a slope. So the slope is 1 divided by delta. And then we make delta to 0. We make them closer, closer, closer. This one becomes 0, so this one goes to infinite. So they closer, closer, become longer, longer, longer until we reach the value. So this is how we conceptually approach our delta function, not really finding a slope at the point. So this is actually defined conceptually. So we define two important functions: step function and unit function, delta function. Delta function and unit function have a relationship that differentiation of unit function is delta function. Subtraction of subtraction of unit function becomes delta function. The other way, if we integrate delta function, there will be unit function, right? Differentiation, integration. If we add our delta function, there will be our unit function from minus infinite to infinite. Because even though, think this way, even though we add them together, let's say we start I made a mistake. Here is n. So this is kind of nonsense, because let's say we have n of minus 2. So this n becomes minus 2, so we're adding from minus infinite to minus 2. From minus infinite, if you add them together, they're still 0. When n is minus 2, they're still 0. So this unit function at minus 2 becomes still 0. If you increase n one more time, minus 1 or 2, they're still 0. Because even though we're adding minus 1 point, they're still 0. When we hit 0, n equals 0, which becomes n, this n becomes 0. u0 becomes 1. Because we hit this point. And after that, if you have n equals 1, u1, we adding them all together, still 0, 1, v becomes 1, and then still 0. So after you add them together, when n becomes larger than 1, still we are not adding anything. We only add 1, value of 1, when we pass n equals 0. So they are corresponding like this. Here, also same, from minus infinite to t. If you keep on adding, so integration is also addition. Okay? If you keep on adding like that, you will have a peak, and when you pass 0, and then you still don't have anything afterward. So you can define them like this.